Thank you very much. And it's always a great opportunity to speak in conference in Brazil, even if it's not in presence. So I hope that my connection will be good. If not, just let me know, please. So the idea of this talk, well, first of all, this is a joint work with Chen Chan. And the idea of this talk is that we want to consider more general things than just symplectic manifolds. For many purposes, symplectic manifolds are not enough. So, for example, singularities should appear everywhere, and you want to include singularities in your picture. And for example, if we think that symplectic manifolds have to do with classical mechanics, then maybe you also want to include more things like fermions in your pictures or field theories or things like that. And then to deal with this kind of things, you need to consider more general things than just symplectic manifolds. And they are these symplectic stacks, or one version should be the symplectic stacks. So let me give an idea of, or a motivation of what I want to talk today, is that there is a well-known Lie group and Lie algebra functor, the Lie functor, that relates these two categories. And there is something called Lie groupoids that is a generalization of the groupoids that Mateus and Rui were talking about before. And it's conjectured that the infinitesimal version is something called degree NQ manifolds. They are graded manifolds with some differential that reproduce the Lie algebra differential. And what happens is that it's really known for a long time that these degree NQ manifolds accept a symplectic version of them, and they are really interesting because they codify really well-known things like symplectic manifolds or Poisson manifolds or current algebroids. So the question is, what do we have in the global side? What is the idea of symplectic Lie groupoids? What they should be? So if we believe that a zero groupoid is just, a manifold, and that's what it is, then if we put symplectic, just symplectic should correspond to symplectic manifolds. In degree one, there is some kind of correspondence with symplectic groupoids. So Poisson manifolds should integrate to symplectic groupoids, even if this correspondence is not complete. And for current algebroids, I need to say that is not known, I think, but there are many attempts of what should integrate current algebroids, and we can find really different objects or proposals for different mathematicians. So the first part of my talk is just trying to propose something on what to put on Lie groupoids that should mimic this symplectic on Q manifolds. And the second part will be just concentrated on a particular case of the degree 2 thing. That is the easiest case of a current algebroid, that is just a current algebroid over a point, and that's a quadratic Lie algebra. So it's a Lie algebra, and though with an add invariant and not degenerate symmetric pairing. It happens that, you see, normally we think that symplectic structures are, skew symmetric, and now I'm talking of a symmetric pairing. But the fact that these graded manifolds are graded and they carry some degree, then some signs change, and this is why the pairing corresponds to a symplectic structure. The symmetric pairing corresponds to a symplectic structure in this graded sense. So that's more or less the structure of my talk. Talk a bit about the first part, what symplectic Lie groupoid should be, and then try to integrate quadratic Lie algebras. So let me make something more or less really crash on what Lie groupoids are. So basically, Lie groupoids are a particular kind of simplicial manifolds. So what a simplicial manifold is a bunch of manifolds and maps among them satisfying simplicial identities. So another way to say what a simplicial manifold is a functor from the category of order of the cardinals to the category of smooth manifolds. And basically, the idea is that these are the faces of the simplices, while the S are the degeneracies of the simplex. And now there is just a really concrete way of saying what Lie groupoids are, that are just simplicial manifolds where the Hall maps are submersions or diffeomorphisms. And you need to think that these conditions, well, these Hall maps is just, on the level I delete all the faces that contain J. So that's what this lambda ij means. And this Pij is the Hall map, and this is just the projection. And this cheap way of encoding what a group is, for example, in degree 1, and this submersion and diffeomorphism condition told us that, you can multiply things. That's basically given by the phase maps. And there exist inverse and multiplications depending on if we are in a groupoid, if, the source and the target, what Mateus explained it in his talk. So all that conditions are encoded on some geometric conditions on the Hall maps that are this, call it as well, Kant conditions. So probably you find it a bit strange, and I think that it's normal. They are not natural, but they are useful, and I will try to convince you during this talk. So associated to each Lie groupoid, we have another simplicial manifold that is just the tangent. I can take just the tangent of each manifold.
Miguel,
Yeah.
I have a question. In your definition, these manifolds xi, they are Banach manifolds? They are infinite dimensional, no?
So right now, I will assume that they are finite dimensional, but it's really that will appear infinite dimensional things at some point, and then things you need to take care. And in that case, I will work with Banach manifolds. Yeah.
And in that case, will there be some condition on these submersions?
Yeah, that's right.
Are they like split submersions, or?
They are, yeah, it's more subtlety. You need to find something that you can lift. It's something technical. I can we can discuss it later if you want. But yeah, there are some particular conditions there.
Thank you.
So yeah, please, if there are more questions, just interrupt me. So associated to each Lie groupoid, I can create another manifold that is the tangent, and this is just taking tangent, applying the tangent functor to everything. And it happens that this tangent, I can select something more concrete, that is this tangent complex, that is just determined by the kernel at level I, by the kernel of the last Horn map that I have, and then I reduce, or I just consider them at the level G0. So how I do that, I look into G0 inside of GI via the first degeneracy map always, and then G0 is inside of each GI, and then I can restrict the kernel of this tangent to that submanifold that I'm still calling by G0. And it happens that these are vector bundles over G0 because I'm taking just the restriction to G0. And also it happens that this is a graded vector bundle with a differential given by the last phase map. And this is what is called the tangent complex. And since it's a complex, I have some homology groups associated to that complex. It happens that for Lie groupoids, since, if I is greater than n, they are diffeomorphisms, then I just can make the tangent complex is concentrated in degree 0 to n. Now, associated to the tangent complex, associated to any groupoid, there is a bicomplex that is the RAM, that is just, in this direction, the RAM, and then in the simplicial direction, I just make the differential given by the pullback of the phase maps. And then I have a total differential that is this global D. And it happens that I can call it right now what a Q form shifted by M is. And this Q form shifted by M is just a collection of forms, let's say in the total complex, but you see there is some truncation. And it means that in degree M, so that at the level M, so the form that sits on GM, it have degree Q. And this is why it's called a Q form, and I don't have higher. So in degree M plus 1, I don't have anything. I just have forms in degree M, M minus 1 till degree 0. So I know that it was really fast and probably not understandable, but it's what I need to say in order to define this M-shifted symplectic Lie groupoids. So associated to any 2 form, I have a 2 form in the degree M, and I can associate something that we call the IM pairing of the 2 form. That just depends on the 2 form on the top level and is given by this strange formula that already appeared in an unpublished notes of Ezra Getzler. So what we can say is that if the 2 form is closed, then this lambda, this IM pairing is invariant under the differential on the tangent complex, because these are vectors in the tangent complex. And therefore, if it's invariant under the differential of the tangent complex, descend to homology. And now I can make finally the definition of what an M-shifted symplectic Lie groupoid is. And is just a Lie groupoid endowed with a M-shifted 2 form satisfying 3 conditions. The first one is that it's closed. The second one is a simplicial condition, that it respects the degeneracies. And the third one is a non-degeneracy condition of the IM pairing. So you see, this pairing should be considered as omega sharp. And what we order or what we demand is that this pairing is non-degenerate just at the level of homology of the tangent complex. You can also demand a strong non-degeneracy, that is non-degeneracy on the tangent complex, but that normally will be too strong. So we just recall being non-degenerate at the level of the tangent complex. Okay, so with that, I need a second question to introduce, that is what symplectic Morita equivalents are. So this was already appearing in the talk of Rui, and basically what they are is the right thing of how symplectic groupoids define when 2 M-shifted symplectic groupoids define the same symplectic structure. So at the end, the symplectic structure will be in the differentiable stack or in the N differentiable stack, that is the Morita class of each symplectic groupoid. So how we define it is by using hypercovers that have a really similar condition to the definition of Lie groupoids. So there are just some surjective submersions somewhere. And then what we want is a zigzag of things of, I have, on the 2 extremes, 2 symplectic groupoids, then I have 2 hypercovers, another N groupoid in the middle, but the middle thing, the only thing that it has is an M-1 shifted 2 form, such that controls the difference of the 2 things by an exact term of D of something. So this kind of formula also appeared really similar, but it has 0 at the end of the Ruiz talk, and right now we have like an homotopy term that is D of this phi. So these are the symplectic Morita equivalents that we define it. And with this, I'm ready to tell you some examples of which kind of things there exist. So the first thing is this diagram over here. We can divide it, our region, into 2 coordinates, the M shifted for the shifted of the symplectic form and the N for the structure of the groupoid. So it happens that, in the gray area there are no symplectic there are not shifted symplectic Lie groupoids. So we couldn't find anything there. And this is because of the non-degeneracy condition. On the yellow area, we can find the structures, but they are particular cases because, you know, the N is smaller than the M. That means that any N groupoid can be considered as an M groupoid. And this is what the arrow A indicates. So they are particular examples of what is happening in the diagonal. And then there is the green area that they are, you know, something that it's including singularities into what is happening in the diagonal case. And singularities in a crazy way. So let me give some examples. On the first column, for example, when M is equal to 0, we have that zero shifted symplectic zero groupoids are symplectic manifolds, but zero shifted Lie groupoids, they are, you know, the groupoid of a foliation. I have, for example, the holonomic groupoid, or, you know, the monodromic groupoid of some foliation, and I have a form on my manifold that is invariant under this foliation, and I should require some non-degeneracy just, you know, on the transversal directions of the foliation. And I think that if I understood it more or less right, if we ask the groupoid to be étal, then we should recover the symplectic gerbs of Rui or something close to that. And if instead of groupoids, I go to two groupoids, I can include more singular things. The second example is, you know, in the second column, M just equal to 1. And what it appears here is presymplectic groupoids, also known as quasi-symplectic groupoids. And in particular, we have that symplectic groupoids are here in the 1, 1. But for example, what we also know is that Poisson manifolds are not always integrable to a symplectic groupoid, but they are always integrable to something that is a one-shifted symplectic Lie groupoid. So that's another really interesting example. And now we have a way of defining what Morita equivalents between non-integrable Poisson manifolds are, for example. And then the third example, that is what I want to discuss, is the next column, just the easiest example that we can have, that there are these pink dots over here, that is where the integration of a quadratic Lie algebra will live over there. Okay, so right now, let me say something. So the first thing, as I was mentioned, is that I wanted to create something that differentiating will be like symplectic Q manifolds. And what happens is that it's wrong. So what we created, even if the Lie functor is conjecture, even in degree 1 that the Lie functor is well known, we have something that is more general than symplectic Q manifolds. And even if we just ask for a strong non-degeneracy, our things, these one-shifted symplectics Lie groupoids are more general than degree 1 symplectic Q manifolds. So maybe symplectic Q manifolds is too strong thing, maybe. That's my conclusion. The second thing, yeah, is that the definition that I give of Morita equivalence was using hypercovers, but there is a definition of, in terms of bi-Hamiltonian spaces, in the case of degree 1, 1, given by Pinshu, and I think that our definition coincides. So the important thing is, in our definition, there is no non-degeneracy condition, and Pinshu have a non-degeneracy condition. And the third thing, as I was saying, is that we can right now define Morita equivalence for non-integrable Poisson manifolds, because they are always integrable as one-shifted Lie groupoids. And then is our definition of Morita equivalence the same as the one given by Joel Villatoro, for example? I also don't know. But these are questions that I hope they are solvable and we can solve it. Just we need time to work more on this. So let's go to the second part of my talk. now what I want to just is to integrate quadratic Lie algebras, that there will be like two shifted something Lie groupoids. So the first thing is that a Lie algebra is always integrated by a connected and simply connected group. Then what is happening is that if the Lie algebra have a pairing, I can create this two form given by this formula and the one form given by this other formula. So the one form, this is also called it, oh, come on, how is called this? The, I don't remember right now, whatever.
Cartan freeform?
Oh yeah, the Cartan freeform, thank you very much. That's the Cartan freeform. And the other two form was appearing in works of Brilinski, Weinstein. And the only thing that we need is just the Maurer-Cartan one form. And the proposition is that this is a two-shifted symplectic Lie group, and it has really nice properties. The first thing is that it's universal in some sense. So this model is the one truncation of the universal integration of a Lie algebra, as given by Andre Enriquez. The second property is that the Lie functor give back the Lie algebra, and now if I apply the Van Est map to this cocycle, and this Van Est map is a generalization that was given by Marius Kreinig and Camilo Arias-Abad, then if we apply the Van Est map to this two form, then we get minus the pairing. So it's really an integration. So in this case, we can check it that it's an integration of the quadratic Lie algebra. And the other nice property is that BG appears as the differentiable stack of this groupoid, of this group in this case. And it happens that then we have a 4 class on the singular cohomology of BG, and this corresponds to the first Pontryagin class. So it's something super classical, and this was known and super nice. So this model, it has really nice properties. So now let me go to a second model. I don't know how much time do I have, but I hope I will have enough.
So Miquel, you have 7 minutes.
Okay, great. Well, yeah, that's great. Thank you. So the second model is infinite dimensional. As Rui was saying, in this case, the definition of Lie groupoid, you need to be a bit careful about how you define it. It's not completely obvious, but in this case, we need to fix some Sobolev class on the kind of path that we are considering. And then the phase maps here in the level 3 going to 2, I consider a loop, and I divided the loop into 3 parts by considering the point 0, 1/3, and 2/3. And the phase maps are given by this division of the loop into 3 parts. It's not completely obvious that this is a group, you need to work a bit. And then it happens that the base loop space of a group, it was known that if the group, it carries an invariant pairing, then the base loop have a symplectic form. And this is this omega2 that we have. And this was, defined by Siegel really many years ago. So it's a really well-known classical stuff. And as you see, also includes the Maurer-Cartan forms. And our contribution is that this is a two-shifted symplectic Lie group, and also have some nice properties. The first one, it appears as a universal integration, but right now of the two truncations, so I consider the Lie algebra as a Lie algebra trivially, and I truncate it, and this is what it appears here, the groupoid that it appears. The second thing is that the Lie functor doesn't sense. In this case, we can also compute it, the Lie functor for this groupoid, and it doesn't sense to the Lie algebra, but sends to a Lie algebra that is Morita equivalent. And we cannot say anything because we need a Van Est map for Lie algebras or for Lie groupoids that is missing. But I'm working with that with Camilo Angulo, and we can say that in this case, give what should give as well, up to Morita equivalence. And the third nice property of this model is that we can obtain the two-level by symplectic reduction from the Chern-Simons sigma model on a disk. And this symplectic reduction is just flat connections on a disk, modulo gains transformations that preserve the boundary in this case. And therefore, we have a symplectic structure, and this is the loop, the base loop group. And the last thing is that there is a frequentization of this symplectic structure given by the string G, and this gives to vertex algebras and Kac-Moody, affine Kac-Moody Lie algebras. So it's really interesting, and this is, a two-gerb, as Rui was saying, and probably, well, not probably, sure, the prequantum bundle should carry a connection whose curvature is given by this two form if it's integrable class. And the last model that I want to define is not always existing, just exists for many triples. So we need to assume that now the Lie algebra, it's split into two parts, into two Lie subalgebras that they are isotropic. They are called Lagrangian subalgebras, and this is what is called a Menin triple. Then it is well known that these Menin triples integrate to a similar object that is called a double symplectic Lie groupoid. So this is a Lie groupoid that is a groupoid in the two directions over H minus and H plus, where H minus and H plus are the integrations, are the source simply connected integrations of the H minus and H plus Lie algebras. And then the space what is appearing is this gamma H over here, and the symplectic form is explicitly as well given by, you see, just the Mauret-Cartan's one forms as before. Then Meta and Tang prove it that they can obtain a local Lie groupoid from this double symplectic groupoid. And then what is happened is that this Lie groupoid, it carries as well a two-shifted symplectic structure. And I can say that if one of the Poisson Lie groups, because H plus and H minus, then H plus become a Lie algebra and H minus, if one of them is complete, then this Lie group, this local, becomes a global Lie group and is a, this semi-direct, well, this double is called the Dreamfield double in this case. And then it's isomorphic to G canonically. So finally, I have three models, and I can give the main result that we have. That is that the three models are symplectic Morita equivalent. And the symplectic Morita equivalent is non-trivial, but in both cases, what we put in the middle is one of the factors, and we have the identity in one case. And then in the infinite dimensional case, we have evaluation at the last point, basically. That's the hypercover that we find it. And then the symplectic form so what makes the homotopy between the two symplectic forms is just the symplectic form, but consider it in the path space. And for the finite model, what makes the homotopy is this beta that is, how the two factors interacts one with the other. So I find it pretty interesting, and the result, and the last remarks that I want to say is just, all the models are different, but all of them are interesting for different reasons. Yeah, there is a previous result relating via some evaluation map, the symplectic form on the base loop group and the two form on the finite group. And this was done using Dirac geometry instead of these Morita by bundles that we use it. And yeah, there is still the question about what I can say about general current algebroids. Can I integrate them? Which kind of models do we have? Are the different models already proposed Morita equivalent? So I don't know so much, but this is what we are working right now. So thank you very much for your attention.